So I don't know back. Okay. Column. Big one this week. Powers and logs.
Powers and logs? You have to sit down.
It's a good time to, we're just starting the chapter with powers.
Alright,
Alright, page 58 please. I know, but I don't think it's a bad idea if I go over it again. Yeah, because she said she did the log one, but not the power one. So it's easier if I just do both. Okay, so if you listen up. Come on, hurry up. So normally I say power or powers, but some books might say indices, okay? So I'll say mostly rules of power. Okay, so you all know what powers are anyways. I mean, you've seen them before. This is x squared, and we've seen this in quadratic equations. And then this one here, x cubed, and you've seen it in cubic equations, yeah? So what we're going to do is we're going to look at the basic rules for powers, and we'll do the proofs as well since they're not so difficult. So the first rule when they multiply together like this, x power n times x power m, that's x power n plus m. Okay, so that's our first rule of powers. Yep. The proof is pretty short. So here I have xn multiply xm. So as you know, this is x multiply itself n times, very good. And then this one here is x multiplied by itself m times. So you can clearly see together you have x multiplied by itself n plus m times. So it's not even a proof really. It makes perfect sense that this is what the rule should be. So this is the first rule. Okay, can I scroll down? Yes? Okay, so the second rule xn over xn, that's xn minus m. And again, the proof is pretty easy. On the top, we have xn times, and then on the bottom, yeah, there's m times here and n times here. And we can cancel them one by one. And each time we cancel, we make one less. So we'll only be left with n minus m on the top after we cancel with all the m's of them on the bottom. So again, there's not much to say about the proof, but that's the second rule there. Okay, have you got the second rule? Yep. Okay, so rule 3. X with a power, and then to power again. Does anyone know what happens here? Very good, they multiply, yeah. So, n multiply n. And the proof is not so difficult as well. We have xn. And how many of these do we have? We have m of these. M of them, okay, of m of xn's. And then inside each of these xn's, how many x's are there? There's n of them. So there's n in each of these. And then how many of these do I have? M of them. So I have, in other words, n plus n again, plus n again, and so on. And how many of these? There's m of these. So if you add a number to itself m times, it's the same as just multiplying by m. Something we saw when, I can't remember, we did something recently where you have to use that result. I think it was proving the arithmetic sum formula. Okay, well, what's most important here is the rule 3. So do you have that one? Yeah, okay, so rule 4. Nth root of x is the same as x power 1 over n. Now this one actually is not too difficult to prove using our last rule, rule 3. If I put a power m on both sides here, what happens to these powers using rule 3? They multiply and you're just left with 1, so that's gone. If you have the square root of something and you square it, it's gone. If you have the cube root of something and you cube it, again they cancel. So you're left with x equals x, which of course is true. So the proof really uses, you need to use rule 3 to prove rule 4. So it's not too difficult to prove.
Do you have to prove it?
No, but like I said, it's not even really a proof. It's just good to know why it works that way. Okay, you have this one? Yeah? Okay. Rule 5. X power minus n is 1 over xn. And if you want to see the reason why, x power minus n is x power 0 minus n, which is x power 0 over x power n. This comes from rule 2. And what maybe is not clear for everybody is when something is to the power of 0, it's 1. But I'll put those together in a rule here, rule 6 then. X power 0 is 1, 0 power x is 0, so anything to the power of 0 is 1, 0 to the power of anything is 0, so does anybody have any ideas what 0 power 0 might be?
1. Over 0. 0.
Go ahead.
1. 0. 0.
1. Error?
No. About 0.
Error was actually the right answer. 0 power 0 isn't defined. It has no value, okay? So this one here is not defined. But these two are. You got them? Okay, so now that we have our 6 rules in place, we can have a look at some examples. Sorry, can I go down? Yeah, so, our first example, nice and easy. We want to simplify this. Well, what rule do I need to use? First rule. Yeah, just add 6 and 2 together. So let's move on straight away to a more difficult one. Without using our calculator, we want to simplify this. Okay, so now we're getting into more difficult ones. Well, just before you start, it's important for me to say that there are many different ways to go through this one, okay? You can use the rules in different order, it's not a problem. So I'll do this one way, and then someone will say, couldn't I have used this rule at the start instead? And the answer is probably yes, okay? So there are many different paths you can take here. If you look at this, what's the first thing you might want to do with it?
81 and 3 goes up.
Yeah, you can see that at least you can do something with the 81 and the 3. So that's what we'll do first. What's that now? 27, isn't it?
Yes.
Okay, now we have choices to make what to do next. I can think of two different things we can do next. No calculator, resist the urge. What do you think?
3 to the power.
One sec, yeah?
3 to power 3 or 9.
Yeah, do something with the 9 maybe, yeah? 3 power 2.
2.
Yeah.
And 3 to power 5 or 4 or 2 4.
You feel like 2, 4, 3 can be a 3 power. I think you're right. So if I go to the side here, let's use our 3. 2, 4, 3 is 3. And what's that? 81, yeah. And then that's done. 81 is 9 by 9. And 9 by 9.
3 by 3.
So, yeah, you're right. It's going to be 3 power 5.
5.
So this is 27 cube root 3 squared all over cube root 3 power 5. Okay, what's next then?
3.
Yes, I know what you mean.
2 over 3.
You have two choices here. As who said, we could put this together.
Yeah.
27 cube root 3 squared over 3 5, because these are both cube roots. So we can just put as one cube root. Okay, which rule to use now?
Rule 2.
The second rule.
Yeah.
So this is 3 power what?
Minus 3.
Minus 3, yeah.
Now rule 4.
Rule 4. Change this into what power?
Minus 3 is 1 over 3.
1 over 3.
Yeah. Minus 1.
Rule number, which rule to use next now? What rule is that?
And we multiply.
Yeah, what number rule?
3 maybe.
Yes, 3. 27 3 power minus 1. Now 27 though. What's
No,
20?
Rule 1 we use.
3
3.
times 3 minus 1.
3 to 2.
Try again.
3 to the power.
Wrong word. Squared. 9. Now check on your calculator. If you do get 9, then you know you've gotten it right. Yeah? Yep, okay. Let's look at one that's more difficult because we don't have numbers in it. So next example, z power minus 1 square root z power minus 3 over z power minus 1 z power minus 5. Now, this is very nice because here I can cancel those straight away. What's next?
We Z0.
Yeah, well, I can put this under one large root. And then I can use which rule?
-5.
Second rule, thank you, -5. So that would be Z squared, which is Z squared power a half, because the square root. Z. Next example. Can I go down? So for this next example, what I need to do is to expand. What I want to do here is to expand and write this as powers of x. So just have everything as a power of x. So what rule do I use to expand the numerator? What do I use to expand on the top? What's it called? It's something to do with a triangle, doesn't it? Pascal's triangle, yeah. So on the top we get 1 plus 2x plus x squared all over x, which is 1 over x plus 2x over x plus x squared over x, which, if you want to be really clear, is x0 over x1 plus 2x1 over x1 plus x squared over x1. You see what I did? Yeah. Which is x power minus 1 plus 2x power, what should I put here? 0 plus x power 1. So that's what they wanted here, is to write it as powers of x. Okay. Next, now there's a very special type of power we have to look at, called the exponential function, or e function. So it's an important constant we want to look at next. This constant here, e. Yeah, e to the power of something. It's an important constant. Roughly, you don't need to remember it that many places, okay? In fact, you don't even have to remember it because it's on your calculator. It's a number like pi, and what I mean by that is it doesn't stop. Okay, I'll just keep going. But it's an important constant. And the reason it's important we'll see at the end of the semester. But for now, it's just a constant for us. Okay? And your calculator has this constant built in it. Can you see? No, not that one. Just look for E.
Alpha.
You might have to press shift or something. On your calculator, I'd like you to calculate this just to practice. What do you get?
7.39.
Do you all know how to do it on your calculator? Because you need to know how to do that, yeah? Yes? Okay. So the last thing to show you now is the graph of this function e. If I want to graph a function like y equals ex. Can I scroll down? Yeah. Okay, so the graph of y equals ex. Now if you want, you could put in different values on your calculator, make a table, and get different points. But the graph will end up looking like this, whatever way you draw it. It'll be very, very flat, and slowly increasing, and then increases quickly. And this here, who can tell me what value this is on the y-axis when x is 0? 1, yeah. Because what's e power 0 is 1. Okay. You can check it. E power 0 is 1. Please note, it does not touch the x-axis. Does not cross the x-axis. Okay, so it's always above the axis. So there's just 4 different possibilities here I want to show you. So this is just ex, but if I go down for a moment, you can have y equals ae bx. Just have different constants in there. So I want to show you the 4 different graphs you get. It depends on if A and B are positive or negative. So the first one is if A is positive and B is positive, A is negative, B is positive, A is positive, B is negative, A is negative, B is negative. They sometimes ask you in the exam to give a quick sketch of these types of graphs. So the first one we just did, if A and B are both positive, like in my last example I had 1e, 1x, so they were both positive, the graph goes up like that. If A is negative and B is positive, the graph goes like this. If A is positive and B is negative, the graph decreases like this. And if A is negative and B is negative, it's like this. These graphs are important, not just in maths but in other subjects too, like in biology for example, because most things grow using this type of graph up until a certain point, okay? And most things decay using this graph as well. So for example, this one here, this is exponential growth, and then this one here is exponential decay. This is something getting small very quickly. Okay. These two here don't really have real world examples. But in the exam, it's one of the 4 which they'll ask you to draw as a quick kind of 2-mark question. They'll say something like this. Can I go down? Yeah. So for example, they might say sketch y equals 2e minus 3x. So very, very quickly, you're supposed to do this. You go x, y, decreasing, and then here, what point is here by the way? Very good. 2, no, try it again. 0, 2. 0, 2, not 2, 0, yeah. Okay? Okay, if you take out your books, I'll tell you which ones to try now. Yeah, you should actually be able to get them done before you go home. So, do for me the last 4 in each. Okay, last 4 in each.